22 days from right now, at 11:16 Universal Time on June 27th, 2026, an asteroid roughly 1 kilometer across will pass Earth at a distance of 2.6 million kilometers. The closest this particular object has come in more than 4 centuries. It will not hit. The orbit is locked. And yet planetary scientists across 3 continents are on what some of them are openly calling high alert for this encounter. The reason has almost nothing to do with what most of the public assume. It has to do with what we are about to see, and what we have spent 29 years not seeing. To understand why this flyby matters, you need to understand what this object actually is, and what is about to be revealed on June 27th. Let's get into it. Drop a comment with where you'll be watching from on June 27th, or whether you've ever caught a potentially hazardous asteroid through your own telescope. Subscribe so you don't miss the encounter coverage as it unfolds. Now let's break this down. 22 days from right now, at 11:16 Universal Time on June 27th, 2026, an asteroid roughly 1 kilometer across will pass Earth at a distance of 2.6 million kilometers. That is 6.7 times the average distance between Earth and the Moon. It is the closest this particular object has come to our planet in more than 400 years. It will not hit. The orbit is locked in by physics that has been understood, verified, and cross-checked across 3 decades of independent observation. There is no scenario inside the next 22 days in which 2.6 million kilometers becomes something materially smaller. You can take that off the table now. The reason scientists are on high alert is not impact. It is something else. And to understand what it is, you have to understand what kind of object this is, where it came from, and why the calendar window between now and June 27th is, in a very specific sense, historic. The asteroid is catalogued as 152637 with the provisional designation 1997 NC1. It was discovered on July 5th, 1997 by an automated survey called the Near-Earth Asteroid Tracking Program, operated by NASA's Jet Propulsion Laboratory in cooperation with the United States Air Force. It has been on the catalogued Near-Earth Object List for nearly 29 years. Across those 29 years, it has been tracked, the orbit refined, the size estimated, the classification confirmed. NASA's Center for Near-Earth Object Studies, NASA's Jet Propulsion Laboratory, and the International Astronomical Union's Minor Planet Center all classify this object as a potentially hazardous asteroid. That term is not a forecast of impact. It is a structural classification that you trigger by satisfying 2 criteria simultaneously, and we will get to exactly what those criteria are in a moment. The point is, this object is on a watch list. It has been on the watch list for nearly 3 decades, and right now, 22 days out, the watch list is about to be put to operational use for the first close encounter that brings the object near enough to actually look at. The numbers around the encounter are precise. The geocentric distance at closest approach is 0.017 astronomical units. In kilometers, that is approximately 2.6 million. In lunar distances, the unit astronomers use when they want a number that makes physical sense to a human listener, that is 6.7. The asteroid will brighten to approximately 10th magnitude during late June. A magnitude 10 object is visible through a backyard 8-inch telescope under dark skies. The brightness will hold above magnitude 11.5 from June 25th through July 1st, giving a clear 7-day observation window for ground-based optical instruments. The asteroid will track across the sky from the constellation Lyra in the northern hemisphere into the constellation Norma in the southern hemisphere, a fast traverse driven by the geometry of the close approach. For 2 days around the peak, observers in the northern hemisphere will have the best view. By the end of the window, observers in the southern hemisphere will be picking it up as it moves south. Now, Here is what the alert is actually about. This object is approximately 1 kilometer in diameter. The exact range, based on its absolute magnitude of 17.9 and an assumed S-type optical albedo, is between 710 meters and 1,600 meters. The central estimate is around 900 meters. So we are talking about a body roughly the size of 1 or 2 city blocks worth of solid rock. An asteroid of that size class, on an orbit of this kind, coming this close to Earth, is approximately a once-per-decade event. And this particular kilometer-class asteroid has never come close enough for human instruments to see it as more than a point of light, moving against the background stars. Until now. The June 27th encounter is the first opportunity in human history to actually image, measure, and characterize what this object physically is. That is what the high alert is about. The window is 22 days from right now. It closes about a week after closest approach. And what happens inside that window is the first photograph of an object that has been tracked, catalogued, and watched for almost 3 decades while remaining, in every meaningful sense, unseen. To understand what is unusual about this object, you have to understand the family it belongs to. Asteroids that cross Earth's orbit are sorted into 4 major dynamical classes, and the class an object belongs to is determined by the shape and size of its own orbit relative to Earth's. The 4 classes are Atira, Aten, Apollo, and Amor. Each one has a different operational signature. Each one creates a different problem for the people whose job is to find them. 1997N C1 is an Aten. An Aten-class asteroid has a semi-major axis smaller than 1 astronomical unit. In plain language, that means it has an orbit smaller, on average, than Earth's orbit. It spends most of its time closer to the Sun than we do. It crosses our path, and we cross its path, but the geometry is not symmetric. An Apollo, by contrast, has a semi-major axis larger than 1 astronomical unit, and spends most of its time outside Earth's orbit. The 2 classes look very different to the people surveying the sky. Apollos pass by us mostly on the night side of Earth, in the part of the sky where ground-based optical telescopes can see them as moving lights against the dark background of space. Atens pass by us, much of the time, on the day side. They come at us out of the direction of the Sun. They live in the part of the sky that telescopes on the ground cannot effectively see, because the Sun itself is in that part of the sky, and it washes out every fainter source for tens of degrees in every direction. This is the operational definition of what the international planetary defense community calls the Sunward blind spot. We will come back to this in detail. For now, the relevant fact is, Atens, structurally, are harder to see than Apollos, and 1997N C1 is an Aten. The orbital elements of this object look like this. The semi-major axis is 0.8648,592 astronomical units, which means the average distance from the Sun is about 86% of Earth's average distance. The eccentricity is 0.2084813, which is a moderately elongated orbit, neither circular nor extremely stretched. The inclination is 16.72286 degrees relative to the ecliptic. That is the tilt of the orbit out of the plane of the planets. 16 degrees is enough that the asteroid spends meaningful time above and below the plane in which all the major planets travel, which is one of the reasons the orbit was not detected earlier than 1997. The orbital period that follows from these elements is about 0.805 Earth years. The asteroid goes around the Sun roughly every 9.5 to 10 months. Every 9.5 to 10 months, in some part of its orbit, it has the possibility of approaching Earth. Most of those approaches are at significant distances. Once every decade or so, the geometry aligns for a close one. June 27th, 2026, is one of those geometric alignments. The object was discovered by the Near-Earth Asteroid Tracking Program, NEAT, a partnership between JPL and the United States Air Force that operated from the mid-1990s through the mid-2000s. NEAT was one of the original automated surveys that turned the search for near-Earth objects from a hobbyist activity into a systematic professional discipline. The program used Air Force telescopes on Maui and at Palomar in California, took wide-field images of the sky on a regular cadence, and used software to find points of light that moved between successive exposures. That is, in essence, how every modern asteroid survey still works. NEAT logged 1997 NC1 in midsummer of 1997. Subsequent observations refined the orbit to a level of precision that allowed the Minor Planet Center to assign the permanent number 152637. The provisional designation, 1997 NC1, encodes the date and order of discovery. The NC portion follows a Minor Planet Center convention for the second half of June 1997. The one at the end means it was the first half-month sequence repeated for this discovery window. None of this is exotic. It is the standard cataloging system. The point is, the object has been in the system for nearly 3 decades. The orbit is well determined. The classification is settled. What has not yet been determined is the most basic physical fact about the asteroid itself. We do not know what it looks like. The two words, potentially hazardous asteroid, carry more weight than people usually realize, and they also carry less. They are technical. They mean something specific. They do not mean what the headlines tend to imply. So we are going to define them precisely, because the entire framing of the June 27th encounter sits on top of this definition. The potentially hazardous asteroid designation is triggered by 2 criteria, both of which must be true simultaneously. The first criterion is an orbital criterion. The asteroid's minimum orbit intersection distance with respect to Earth, the closest possible geometric distance between its orbit and Earth's orbit, calculated at the closest possible alignment of the 2 orbits, regardless of where the asteroid actually is in its orbit at any given time, must be less than 0.05 astronomical units. In kilometers, that is approximately 7.5 million. In lunar distances, that is just under 20. The second criterion is a size criterion. The asteroid's absolute magnitude must be brighter than 22. Absolute magnitude is a measure of how bright the object would appear if it were exactly 1 astronomical unit from both the Sun and the observer, and it correlates with size. A magnitude 22 threshold corresponds to a diameter of approximately 140 meters or larger, depending on surface reflectance. Smaller than that, the asteroid is not classified as potentially hazardous, regardless of its orbit. Larger than that, with the right orbit, the designation applies. 1997 NC1 satisfies both criteria by a substantial margin. The minimum orbit intersection distance is well inside the 0.05 astronomical unit threshold. The absolute magnitude of 17.9 corresponds to a diameter of approximately 900 meters at the central estimate, and the size range extends from 710 meters to 1,600 meters, depending on what assumption you make about the surface reflectance. The asteroid is not borderline on either criterion. It is several factors clear of both. That is why it has been on the potentially hazardous asteroid list for nearly 3 decades. You should pause and think for a moment about why this list exists at all. It is not a paranoia list. It is a list with a legislative origin. In 1998, the United States Congress passed a mandate that came to be known as the Space Guard Survey, which directed NASA to identify 90% of near-Earth asteroids with diameters of 1 kilometer or larger by 2020. The mandate was the result of a specific moment in late 20th century planetary science, when the impact hazard from large asteroids had moved from theoretical speculation to operational policy. The Cretaceous-Paleogene impact had been definitively established at the end of the 1980s. The Shoemaker-Levy 9 fragments had hit Jupiter in 1994, with energies that, scaled to Earth, would have ended civilization several times over. The combination shifted the policy environment, and Congress responded with a survey mandate. The potentially hazardous asteroid classification system came out of that mandate. It was a structural decision, made for structural reasons, by people who understood that you cannot mitigate a hazard you have not first catalogued. 1997NC1 was discovered the year before that mandate became law. It is one of the early objects in the catalog that came out of the survey infrastructure built in response to the mandate. The SpaceGuard mandate, for the record, was achieved late, but it was achieved. By the late 2010s, the cataloging completeness for asteroids 1 kilometer and larger had passed 90%. There are not very many kilometer-class near-Earth asteroids we do not know about. The completeness at the 140-meter scale, the threshold that defines potentially hazardous asteroids, the regional catastrophe size class, is around 40%. The completeness at the meter scale, where Tunguska-size events live, is in the single-digit % range. The catalog is densest at the largest sizes and thinnest at the smallest. The reason it is densest at the largest sizes is because larger objects are brighter, easier to detect, and they cross the inner solar system on orbits that are more stable and easier to predict. 1997N C1 at 1 kilometer is in the high completeness end of the population. We know it is there. We have known it is there for 29 years. The question of the June 27th encounter is not whether we will see it. The question is what we will see when we look. We need to spend a few minutes on the geometry of why Atens are hard to see, because it is the structural fact that explains everything else about the planetary defense story, and it is the reason the next generation infrastructure being built right now exists at all. The simplest version is this. Ground-based optical telescopes are pointed at the night sky. They look at the parts of the sky where the sun is not. The sun is the loudest thing in any wavelength a telescope can see, by an enormous margin. You cannot point a sensitive optical instrument anywhere near it without flooding the detector and losing every fainter signal. The operational consequence is that there is a cone of sky anchored on the sun that ground-based surveys simply cannot search. The cone is typically 40 to 60 degrees wide, depending on the telescope and the observation site, which is a substantial fraction of the entire sky. Aten-class asteroids spend most of their orbital time inside the cone. Their orbits are smaller than Earth's, which means that from our perspective, they are usually somewhere between us and the sun, or on the far side of the sun. When they are on the near side, between Earth and the sun, they are in front of the sun from our point of view. When they are on the far side, they are behind the sun. In both cases, the cone of sky we cannot search hides them. The only time we can see them well is during a relatively narrow window, when their orbital position puts them at an angular separation from the sun that gets them out of the cone. That window is short, and it happens irregularly. For some Atens, it can happen years apart. This is the operational reality the international planetary defense community has been documenting since the early 2000s. Research published in the planetary defense literature has shown that the warning efficiency for asteroids approaching Earth from the sunward direction, using only ground-based instruments, is dramatically lower than the warning efficiency for asteroids approaching from the night side. Some recent modeling has shown that the gap is closable with the right space-based infrastructure, specifically telescopes placed in heliocentric orbits ahead of Earth that can look back at the sunward direction with the sun behind them rather than in front. That kind of infrastructure does not exist yet. 2 missions are designed to provide it. The European Space Agency's NEO concept is one. NASA's Near-Earth Object Surveyor mission is the other. We will come back to both of these. The point I want to make here is structural. Atens, by class, are the asteroids that the existing ground-based detection infrastructure was always going to have the hardest time finding. and 1997 NC1 is an Aten. The reason we knew about it in 1997 is because the geometry happened to be favorable that summer. The reason we have been able to refine the orbit over 29 years is because subsequent recoveries have caught it during those infrequent windows when it stepped out of the cone. The reason June 27th, 2026 is the encounter that finally lets us see the object as more than a point of light is because this time the geometry will not be favorable for a few weeks. It will be excellent. The asteroid will brighten to magnitude 10, sit 20 degrees and more from the sun in the night sky, and remain visible for a clean week. And the next time the geometry is this favorable, this object will be in a different part of its orbital cycle, and the angular separations will be different. And the same kind of opportunity may not present itself for years or decades. The Sunward blind spot ensures that. Which brings us to what is going to be aimed at this asteroid during those few favorable weeks, and what it is expected to find. The Goldstone Solar System radar in California is the most powerful planetary radar facility in the Western Hemisphere. It is operated by NASA's Jet Propulsion Laboratory at the Goldstone Deep Space Communications Complex in the Mojave Desert, and it is one of the small handful of instruments on Earth capable of producing usable radar images of asteroids during close approaches. Goldstone's main antenna for this kind of work has historically been a 70-meter dish, designated DSS-14. That is the antenna that imaged the asteroid Tatatis during its 1992 flyby. That is the antenna that imaged the asteroid 2005 YU-55 during its 2011 flyby. It is the antenna that has done most of the high-resolution planetary radar work on near-Earth objects for the last 3 decades. DSS-14 is offline right now. It is undergoing a major modernization and will not be back in service until 2028. This is a publicly documented infrastructure fact. The implications for the June 27th, 2026 encounter are operational. The Goldstone Radar Observation Plan, published by JPL specifically for 1997 NC1's 2026 encounter, calls for a non-standard configuration. The transmitter will be DSS-26, a 34-meter antenna operating at 7,190 MHz. The receiver will be DSS-13, another 34-meter antenna located elsewhere in the complex. This is what radio astronomers call a bistatic configuration. The transmitting antenna and the receiving antenna are physically separated. You send a radar pulse from one, and you catch the echo with the other. It is not the highest sensitivity configuration available. Monostatic radar from a 70-meter dish is more powerful. But the bistatic configuration with 34-meter antennas is functional, and the published planning document explicitly states that the observation is expected to produce, quote, a rapid continuous wave detection with the possibility of signal-to-noise ratios strong enough for coarse resolution imaging. Translated into ordinary language, Goldstone is expecting to bounce radar off this asteroid, catch the echo, and produce the first image of it that has any resolution beyond a single pixel. That is the photograph. That is what the alert is about. For 29 years, this object has been known as a point of light, a row in the catalog, a set of 6 orbital elements with uncertainties attached. After the June 27th encounter, if the radar observation succeeds at the level the planning document expects, it will become a body with a measured shape, a measured rotation period, and measured surface characteristics. The rotation period of this asteroid is, right now, unknown. For a kilometer-class, potentially hazardous asteroid that has been catalogued for almost 3 decades, the absence of a measured rotation period is unusual. It reflects the fact that this is the first apparition where the object has been close enough and bright enough for the necessary measurements to be feasible. The rotation period, when it is determined, will tell scientists something fundamental about the object's internal structure. If the rotation is faster than about 2.2 hours, the asteroid has to be monolithic, a single solid body, because at faster rotation rates, Centrifugal force at the equator exceeds the gravitational binding strength of a loose aggregate. If the rotation is slower, the asteroid could still be monolithic, or it could be what planetary scientists call a rubble pile, a body that is essentially a gravitationally bound collection of fragments rather than a single solid rock. The distinction matters operationally because rubble piles and monolithic bodies respond very differently to forces applied to them, which means they would respond very differently to any future deflection attempt. The Goldstone observation will not by itself definitively answer the monolithic versus rubble pile question, but it will start to constrain it. Other observations during the encounter window will fill in the rest of the physical characterization. Visible and infrared spectroscopy from optical telescopes will identify the dominant mineralogical signatures on the surface. The current best assumption is S-type composition, which means stony silicates, but the spectroscopy will either confirm that or shift the picture. If the surface turns out to be darker than the S-type assumption predicts, the diameter estimate goes up, potentially toward the upper end of the 710 to 1,600 meter range. Optical polarimetry will measure how the surface scatters light, which constrains the regolith properties. Infrared radiometry will measure the heat emission, which constrains the thermal inertia and the rotation averaged surface temperature. Each of these measurements is a small piece of the puzzle. Together, by mid-July, they will have transformed 1997NC1 from a moving point of light into a characterized physical body. That is the first photograph. That is what the alert is for. And it is the kind of scientific result that makes a flyby a once-in-a-generation opportunity, even when there is no impact risk involved. There is a smaller but important second prize from the encounter, and it has to do with a subtle effect that almost nobody outside planetary science thinks about. The Yarkovsky effect is the name for what happens when an asteroid absorbs sunlight on its day side, rotates that warmed surface around to its night side, and re-radiates the heat as infrared light. The re-emitted infrared light carries momentum. The momentum imparts a small, persistent, directional push on the asteroid. Over a single orbit, the push is tiny. Over thousands of orbits, accumulated across centuries, the push slowly changes the orbit. This is the Yarkovsky effect. For most near-Earth asteroids, the Yarkovsky effect is too small to detect directly in the available astrometric data. For a handful of well-characterized, potentially hazardous asteroids, the data has gotten precise enough that the Yarkovsky drift is the dominant remaining source of orbital prediction, uncertainty for impact risk calculations. There are currently 4 such asteroids on the formerly Yarkovsky tracked list. They are Bennu, the asteroid OSIRIS-REx sampled; Apophis, which everyone remembers from its briefly elevated impact risk during the late 2000s. 1950 DA, a kilometer-class object whose distant future impact possibilities require Yarkovsky modeling to constrain; and 2009 FD, another kilometer-class object on a similar long-term watch. 4 asteroids. 1997N. C1 is not currently on this list. It has not yet had a close enough encounter for the astrometric precision required to characterize Yarkovsky drift on a body of its size. The June 27, 2026 encounter is expected to provide the data that makes that characterization possible. Whether it lands on the formal Yarkovsky watch list depends on what the radar and the precision optical astrometry deliver in the days immediately around closest approach. The probability is good that it will, which means, starting in the second half of 2026, the long-term orbital prediction for this asteroid is likely to get sharper by orders of magnitude. The reason this matters is not that it changes anything about the June 27th encounter. The encounter is locked in. The reason it matters is what it implies for the next several centuries of approaches. 1997N C1 is going to keep coming around. It will not hit Earth in any time horizon currently in the calculation. But every kilometer-class, potentially hazardous asteroid on the books is, by definition, an object whose orbit needs to be tracked across decades and centuries, because the minimum orbit intersection distance is small enough that small accumulated perturbations could, over very long timescales, matter. The Yarkovsky characterization is how you take a kilometer-class object from "we know where it is now" to "we know where it will be in 200 years. That second statement is what the planetary defense community works toward for objects in this class. The June 27th encounter is the data point that makes the second statement possible for this asteroid. And that is the scientific reason this flyby is on every planetary defense calendar for the year. You should know what 1 kilometer of rock actually means in terms of energy, in terms of consequences, in terms of why the potentially hazardous asteroid classification draws the lines it draws. We are going to walk through this carefully because the numbers are important and the comparisons are easy to misuse. To be absolutely clear before we start, 1997 NC1 is not going to hit Earth on June 27th. It is not on an impact trajectory in 2027. It is not on an impact trajectory in any year currently inside the published orbital horizon. The size figures we are about to walk through are not a description of what is going to happen. They are a description of why the classification system treats asteroids in this size class as a distinct category that warrants long-term observation. A near-Earth asteroid hits Earth at a typical relative velocity of about 17 kilometers per second, give or take a few kilometers per second, depending on the orbital geometry. The kinetic energy of a moving body scales with the square of velocity and linearly with the mass. The mass of a kilometer-class asteroid, assuming a typical bulk density of around 2.5 grams per cubic centimeter, appropriate for a stony body, is on the order of 1 billion to several billion metric tons. The kinetic energy at typical impact velocity for a body that massive is on the order of tens to low hundreds of thousands of megatons of TNT equivalent. To put that scale into something humans can hold in their head, the Tsar Bomba, the largest nuclear weapon ever detonated, was approximately 50 megatons. A kilometer-class asteroid impact at typical velocity carries an energy budget equivalent to hundreds to thousands of Tsar Bombas detonating simultaneously at the impact site. That is the regional catastrophe class. An impact of that scale on land would carve a crater on the order of 10 kilometers across, eject material into the stratosphere at quantities sufficient to perturb global climate for months to years, and cause severe damage on continental scales radiating from the impact site. An impact in an ocean basin would produce tsunami chains capable of striking coastlines around the entire basin, and possibly into adjacent basins. The effects are not extinction level. Extinction level is a different size class, but they are well above the threshold at which global agricultural systems would be put under serious strain. For perspective, the Tunguska event in 1908 is the canonical reference for what a much smaller object does. Tunguska is estimated at 10 to 15 megatons of TNT equivalent, attributed to an object approximately 50 to 60 meters in diameter, which exploded in the air over Siberia and flattened roughly 2,000 square kilometers of forest. 1997 NC1 is approximately 20 to 30 times the diameter of the Tunguska impactor. Mass scales with the cube of diameter, so the mass and the kinetic energy budget of 1997 NC1 are on the order of 8,000 to 27,000 times the Tunguska scale. The Chicxulub impactor, the asteroid that produced the end Cretaceous extinction 66 million years ago, was on the order of 10 to 19 kilometers in diameter, 10 to 20 times larger than 1997 NC1. 1997 NC1 is firmly in the regional catastrophe size class, an order of magnitude or more below the extinction class. The classification system, drawing the line at 140 meters for the lower threshold of the potentially hazardous asteroid category, is calibrated to exactly this regional catastrophe threshold. 1997 NC1 is well above that threshold. That is why the classification exists. That is why the asteroid is on the catalog. That is why the June 27th encounter is treated with the scientific attention it is being given. Not because of what will happen on June 27th, because of what could, in some other century, on some other approach, happen to an object in this size class, and because human civilization is currently in the process of learning how to track and eventually defend against that class of object. 1997 NC1 is one of the bodies that classification system was built around. Here is the structural tension that runs underneath the entire June 27th encounter. The international planetary defense community has known about the Sunward blind spot since the early 2000s. The community has been openly advocating for space-based infrastructure to close that gap for the better part of 2 decades. 2 specific missions are designed to do exactly that. NASA's Near-Earth Object Surveyor mission, the European Space Agency's NEO mission concept. Neither of them is operational right now. NEO Surveyor's projected launch is no earlier than September 2027, no later than June 2028. NEO is further out, still in concept development. The June 27th, 2026 encounter of 1997 NC1 happens with neither of them online. The asteroid will be characterized using the previous generation infrastructure, ground-based optical telescopes that cannot effectively see into the sunward direction, Goldstone radar operating with its backup antenna because the primary antenna is offline for modernization, and a community of amateur and semi-professional observatories doing precision astrometry from telescopes one observer can fit in a backyard. The infrastructure built specifically to close the gaps that the existing system has cannot help with this encounter. It is not yet built. NEO Surveyor is the closer-in of the 2 missions. It is a 50-centimeter aperture space telescope designed to operate at 2 thermal infrared wavelengths and to look for the heat signatures of asteroids that ground-based optical telescopes cannot see. It will operate from a Sun-Earth Lagrange point, which puts it in a geometry where it can look back toward the inner solar system without the sun directly in the field. The mission has been under development for years and recently passed its critical design review. The infrared telescope and the instrument enclosure are currently being integrated and tested at Utah State University's Space Dynamics Laboratory. The sunshade, the structure that keeps the infrared detector cold by keeping sunlight off it, is being tested at BAE Systems Space and Mission Systems facility in Boulder, Colorado. These are real physical pieces of hardware in clean rooms being prepared for launch. The schedule says no earlier than September 2027. The earliest possible operational data from NEO Surveyor will be months after launch, which puts the first useful science return into late 2028 at the absolute earliest. The 5-year baseline survey will run from there. By the end of the survey, NEO Surveyor is expected to have found at least 2/3 of the previously undetected near-Earth objects larger than 140 meters. The infrastructure is being built. It is just not being built in time for June 27th, 2026. NEO, the European mission, sits further back in the development pipeline. The concept is to place a single sunward orbiting telescope at the Sun-Earth Lagrange point 1 location between Earth and the Sun, approximately 1.5 million kilometers in the sunward direction from Earth, and to use it to look outward, away from the Sun, with the Sun behind it. That geometry covers the sunward blind spot that ground-based instruments cannot see into. The mission has not yet been formally adopted for full development. It is, as planning documents go, several years behind NEO Surveyor. The honest reading of the situation is straightforward and worth saying without dressing it up. The international planetary defense community has spent more than 2 decades publicly documenting the gap in detection infrastructure and openly advocating for the missions that would close it. The political constituency for these missions is small. Funding has been intermittent. The timelines have slipped. As a result, in 2026, a once-per-decade close encounter by a kilometer-class, Aten-class potentially hazardous asteroid is going to be characterized by the previous generation infrastructure, even though the next generation infrastructure is physically being built right now in clean rooms in Utah and Colorado on a schedule that has it operational starting in the late 2020s. The gap is real, and it is structural, and it is publicly documented. It is not a cover-up. It is a story about how slowly civilization moves to build infrastructure for hazards that operate on geological timescales, while political attention operates on quarterly ones. 1997 NC1's encounter is, in a sense, a test of the current system. The system will perform. The encounter will produce excellent science. But the system that will be testing it is a generation behind the system that is being built to replace it. That is the operational frame. There is a piece of the story that often gets overlooked when professional planetary defense activities make headlines, and it is worth a moment of attention because it represents how the actual scientific ecosystem around potentially hazardous asteroid close approaches functions. During the observation window around June 27th, an independent observatory operating from the Algarve region of southern Portugal, equipped with a 16-inch reflecting telescope, has publicly announced plans to share live observations of the close approach. The observatory has indicated it will image the predicted track of the asteroid below the constellation Ophiuchus, weather permitting, and is actively monitoring for any deviation from the published ephemerides. This kind of independent monitoring is standard practice in the amateur and semi-professional astronomical community, and it complements the professional radar and optical observation programs in ways that are operationally important. The reason this matters is structural. Every major potentially hazardous asteroid close approach is observed not just by the dedicated professional facilities, but by a global community of amateur and semi-professional observers, many of whom contribute precision astrometric measurements that are folded back into the official orbital solutions through the Minor Planet Center. The Portugal Observatory is one data point in this larger ecosystem. The phrase actively monitoring for any deviation in the path is not a hint at suppressed information. It is a statement of routine scientific practice. If the asteroid is exactly where the published ephemeris says it will be, that confirms the orbital model. If there is a small deviation, that deviation is a measurement of forces acting on the asteroid that are too small to detect over shorter baselines. Most likely the Yarkovsky effect we discussed earlier, which is exactly the kind of measurement scientists are hoping to refine from this encounter. The amateur and professional observations work together. The amateur stream provides independent verification and supplementary data. The professional stream provides the deep instrumental capability. Neither replaces the other. The broader point is that the existence of independent observers preparing to track this encounter is evidence that the system is functioning. A truly opaque planetary defense apparatus would not have publicly distributed ephemerides that amateur observers can use to predict where the asteroid will be at any given moment. The fact that an observatory in Portugal can announce a live observation plan with a specific constellation field and a specific monitoring intent is itself a feature of an open scientific ecosystem. That openness is part of why the answer to almost every question about a potentially hazardous asteroid close approach can be cross-checked from multiple independent angles, and why claims that the official story is concealing the real risk tend to fall apart when you trace where the data actually comes from. Which brings us, finally, to the 5 framings that always show up around encounters like this one. A kilometer-class, potentially hazardous asteroid, making its closest documented approach in 4 centuries, occurring inside the operational gap between the current generation of planetary defense infrastructure and the next generation that is being built but is not yet online, is exactly the kind of event that draws speculative interpretation. Some of that speculation is useful skepticism, which is healthy. Some of it is conspiracy-shaped. We are going to take the conspiracy framings seriously, examine what each one actually claims, and then dispatch them against the physics, the data, or the structural realities. There are 5 of them that show up consistently around encounters of this kind. We are going to take them in order. Framing 1. NASA is concealing the actual impact risk. The claim asserts that the official statement of a 2.6 million kilometer encounter distance is a managed message, and that the real probability of impact is being suppressed for some institutional reason. The dispatch is the structure of how potentially hazardous asteroid close approaches are tracked. The orbital elements of 1997 NC1 are publicly published. The ephemerides are open. The Goldstone radar planning document is hosted on a NASA Jet Propulsion Laboratory public web server. The orbital prediction can be independently verified by anyone with access to standard orbital mechanics software, including the amateur observer in Portugal, who is about to do exactly that. An asteroid that was actually on a near-term impact trajectory would not exist inside this kind of open, cross-checkable information ecosystem. The architecture of how the data flows is the dispatch. Concealment is incompatible with the operational reality of an open, distributed, scientific community working in public. Framing 2, the orbit might shift between now and June 27th. The claim asserts that small perturbations could change the encounter geometry enough to make 2.6 million kilometers turn into something much smaller. The dispatch is the magnitude of the available perturbations. In the 22 days between right now and June 27th, there is no interplanet flyby that affects 1997 NC1's orbit. The Yarkovsky effect we discussed earlier, integrated over 22 days for a kilometer-class object, produces an orbital drift of meters, not millions of kilometers. There is no known mechanism, gravitational or non-gravitational, that could change the encounter distance by more than a small fraction of 1% in the available time window. The amateur observer in Portugal will, in all likelihood, see the asteroid almost exactly where the published ephemeris places it. If there is any detectable deviation, it will be small enough to require precision photometry to measure, and that small deviation will itself be the scientific reward, not a danger signal. A measurement of subtle forces that have been understood for a century. Framing 3. The Sunward blind spot is being deliberately maintained. The claim asserts that the slow rollout of dedicated Sunward detection infrastructure is structurally deliberate, intended to leave the Sunward direction unmonitored for some strategic or institutional reason. The dispatch is the public funding history and the open mission documentation. NEO Surveyor passed its critical design review in 2026. Its hardware is integrating at Utah State University's Space Dynamics Laboratory. Its sunshade is at BAE Systems in Boulder, Colorado. These are public-facing facts with budget lines, contractor names, technical documentation, and physical artifacts in clean rooms. The honest read is that the planetary defense community has been openly documenting the Sunward blind spot for 2 decades, openly advocating for missions to close it, and openly underfunded because the political constituency is small. The gap is not maintained. It is what slow institutional movement looks like when the threat operates on timescales longer than budget cycles. The publicly available record is the dispatch. Framing 4. Independent observers know something official agencies are hiding. The claim asserts that the amateur and semi-professional observatories preparing to track the asteroid live are doing so because they have reason to expect a deviation from the official ephemeris. The dispatch is what the observers themselves are actually doing, and why. Independent monitoring of well-catalogued, potentially hazardous asteroids is standard practice in the amateur community. It is a service to the scientific record. The observation plans around the June 27th encounter are a routine, expected element of how the asteroid science ecosystem operates. The presence of independent observers is evidence that the system is healthy and open. It is not a hint that the system is hiding something. Asking what independent observers are looking for is the right question. The answer turns out to be They are looking for the same precision astrometric data that the professional facilities are looking for, and they are doing it as part of a coordinated, transparent contribution. Framing 5. A kilometer-class asteroid passing this close must have some hidden meaning: astrological, prophetic, or paranormal. The claim asserts that a once-per-decade event of this scale is somehow correlated with terrestrial events in a way that is not currently recognized by mainstream physics. The dispatch is the energy budget. The gravitational tidal force exerted by an asteroid of this mass at this distance is many orders of magnitude smaller than the tidal force the Moon exerts on Earth every day, and many further orders of magnitude smaller than the tidal force exerted by the Sun. There is no known physical mechanism by which a close approach at 2.6 million kilometers could produce any measurable terrestrial effect. Not on the atmosphere, not on the oceans, not on the lithosphere, not on the biosphere. The astrological framing is dispatched by the absence of any plausible coupling channel between the asteroid and Earth. The asteroid will pass, and nothing on Earth will change as a result of its passage. The thing that will change is what scientists know about the asteroid. 5 framings dispatched. The encounter prediction is solid. The structural gap in detection infrastructure is real, but is not a cover-up. The independent observers are doing routine science. The asteroid will not, by any mechanism known to physics, affect terrestrial events. What is left is the actual scientific story, which is what we are going to spend the rest of this video on. By the time the brightness window closes around July 1st, the scientific yield from the June 27th encounter will fall into roughly 5 categories. We are going to walk through them in order of how much they will tell us about the asteroid as a physical body. First, shape. The Goldstone radar observation, even at the coarse resolution the planning document anticipates, will resolve 1997 NC1 to a small number of pixels. From those pixels, combined with the geometry of the encounter and the modulation of the radar echo as the asteroid rotates, a first-generation shape model becomes feasible. The shape may turn out to be approximately spherical, which is consistent with what we would expect from a large body that has experienced enough collisional history to round out. It may turn out to be elongated, which is consistent with a body that has experienced disruption events, but not enough subsequent gravitational settling to fully round out. It may turn out to be a contact binary. 2 bodies touching at a single point, the geometry that asteroid 2014 MU69, Arikoth, visited by New Horizons, presented. We will not know the answer until the radar data comes in. The shape is the first thing that opens. Second, rotation. Once the shape model is in place, the light curve modulation observable in the optical photometry, the way the asteroid's brightness varies as different parts of its surface rotate into and out of view, will pin down the rotation period. As we discussed earlier, a rotation period faster than approximately 2.2 hours implies a monolithic internal structure. A rotation period slower than that is consistent with either monolithic or rubble pile structure, but does not by itself resolve which. The most likely range, based on what is known about kilometer-class near-Earth asteroids generally, is somewhere between a few hours and a few tens of hours. The actual answer will be determined by data, not assumption. Third, surface composition. The visible and infrared spectroscopy planned for the encounter will identify the dominant mineralogical signatures on the asteroid's surface. The current assumption is S-type, silicate-rich, stony, and the spectroscopy will either confirm that or push the classification in a different direction. If the surface turns out to be substantially darker than the S-type assumption predicts, the diameter estimate goes up, potentially toward the upper end of the 710 to 1,600 meter range. If the spectroscopy reveals carbonaceous material on the surface, the picture changes again. The composition is operationally important. It tells you about the asteroid's history and its origin in the asteroid belt. It also tells you about how it would respond to potential deflection methods, because impactors react differently to stony bodies than to rubble piles, than to carbonaceous bodies, than to metal-rich bodies. Fourth, the Yarkovsky drift. The astrometric precision available from the close approach. What the radar timing provides, combined with what the optical observations provide, is expected to be sufficient to detect the small accumulated effect of Yarkovsky thermal radiation on the asteroid's orbit, integrated across the time baseline of all observations to date. As we discussed earlier, this is the measurement that would put 1997NC1 onto the formal Yarkovsky watch list, with Bennu, Apophis, 1950DA, and 2009FD. The probability is reasonably high that the measurement will succeed. Once it does, the long-term orbital prediction for this asteroid, out to the next several centuries of close approaches, sharpens by orders of magnitude. Fifth, the long-term implications for planetary defense data architecture. The June 27th encounter is one of a relatively small number of opportunities each decade to fully characterize a kilometer-class potentially hazardous asteroid. Every successful characterization adds to the global database that planetary defense planners use when they ask questions about what the worst-case scenarios actually look like for objects in this class. 1997N C1's data goes into that database. It informs decisions about which objects need closer monitoring, which objects need radar follow-up at subsequent apparitions, and which objects need physical sample return missions of the type OSIRIS-REx flew to Bennu. The encounter is, in a sense, an instrument that takes a row in a catalog and turns it into a fully characterized scientific target. Not every kilometer-class potentially hazardous asteroid will get this treatment in any given decade. The ones that do are the ones whose orbital geometry happens to align. 1997N C1's geometry aligns on June 27, 2026. That window will close. The next equivalent window for this specific object is in the next decade. The data gathered between June 25th and July 1st of this year will inform what scientists know about this object for as long as anyone is paying attention. So when the original framing of this story is scientists on high alert, it is worth asking precisely what they are alert to. They are not alert to impact. The impact picture for June 27th, 2026 is settled. The asteroid will pass at 2.6 million kilometers. The encounter will be safe, and there is no version of the available physics in which this changes. They are not alert in the sense of the operational alerts that the planetary defense community uses for actually concerning trajectory uncertainties. There are none of those for this object. What they are alert to is the rarity of the opportunity. A kilometer-class, Aten-class, potentially hazardous asteroid is one of the harder to characterize categories in the catalog. It lives in the Sunward blind spot most of the time. Its rotation period is unknown after 29 years of cataloging. Its shape is unknown. Its surface composition is assumed but not measured. The June 27th encounter is the first opportunity in human history to find out what it actually is. The window is finite. The instruments that will measure it are themselves operating in a moment of infrastructure transition. Goldstone with its backup antenna because its primary is offline for modernization. NEO Surveyor in clean rooms but not yet launched. Neomir still in concept development. The alert is to make sure that the existing infrastructure is mobilized to extract as much scientific value as possible from the encounter, because the next equivalent encounter for this object is on the order of a decade away, and by then, ideally, the next generation infrastructure will be in place to do better than what is possible right now. There is a longer arc version of the alert that is worth saying clearly. Civilization is, slowly, building the capacity to detect, track, characterize, and eventually intervene against kilometer-class threats to the planet. The DART mission which deliberately impacted asteroid Dimorphos and altered its orbit, was the proof of concept for deflection. The SpaceGuard survey, which catalogued more than 90% of the kilometer-class near-Earth asteroid population, was the proof of concept for systematic surveillance. NEO Surveyor, when it launches, will be the proof of concept for Sunward direction detection. NEO, when it launches, will extend that capability. Each one of these is a piece of the long-term infrastructure for handling the kind of object 1997 NC1 represents. None of them, taken individually, is sufficient. All of them, taken together, are what a serious civilizational response to the asteroid hazard actually looks like. The June 27th, 2026 encounter is one data point in that larger story. It is a routine flyby. It is also, scientifically, the most important opportunity to characterize 1997 NC1 that has presented itself since the asteroid was discovered. The way to think about the next 22 days is this. The asteroid is approaching. The orbit is locked. The geometry is favorable. The instruments are ready, including the ones operating in non-standard configurations, because their primary modes are offline for maintenance. The amateur and professional observation programs are coordinated. The encounter will happen at 11:16 Universal Time on June 27th. The brightness window will run from approximately June 25th through July 1st. By the second week of July, the first results will start to appear in the public scientific literature. By the end of the summer, the shape model and the rotation period and the surface composition will be settled. By the end of the year, the Yarkovsky measurement will likely have been published, and the long-term orbital prediction for 1997 NC1 out to its next several close approaches across the next century will sharpen. There will not be a moment of dramatic revelation. There will be a quiet accumulation of measurements that in aggregate will transform a point of light into a known body. The asteroid will keep coming back. The next equivalent encounter is a decade or more out, and by then, the infrastructure will be different. The asteroid will be the same one we are about to look at, except by then, we will already know what it looks like. June 27th, 2026 is the day we find out. The real question is not whether the asteroid will hit Earth. It will not. The real question is what humanity does in the years that follow. When the data is in, the characterization is complete, and the next generation of planetary defense infrastructure is, finally, online. The encounter is the photograph. What the photograph means is up to us.